This lesson is for section 13.4. We're going to be talking about rational and irrational roots. Our objectives for today are to find all the roots of a polynomial equation, as well as to simplify powers of I. Now this is going to be a slight bit of review for you, but it is important for me to go over stuff from last year because there's a little tricky stuff that you're going to have to remember from last year's algebra class. So let's get started with the rational roots theorem. Now the rational roots theorem states that for any polynomial equation of this form, okay, which we've been working with the last few sections, you can find any possible rational root for this equation if you list all of the factors of p over q. Now we'd have to first define p and q, so let me do that. So first you're going to find all the factors of a sub 0, this term here, all the way at the end. This is going to be a constant. Okay, so you would list all of the factors of this value, which we're going to call p. Okay, here's our p value. Now our q value comes from the lead coefficient here, a sub n. Your lead coefficient is, of course, also a constant, but I'm going to refer to that as the lead coefficient. So you're going to then list all of the factors of a sub n, and we're going to call this q. So a sub n is q. Then what you do to find a list of all of your possible rational roots is take p over q and list all of those values. So these would give you the list of all possible rational roots. Now this is something that could be really tedious to have to test, because you're going to get a really long list. Even for sometimes a really simple equation, you might get a really long list of p over q values. So that's why this next theorem comes in handy. Okay, so the upper bound and lower bound theorem is something that comes in handy so that you don't have to test every single rational root. Because basically what it says is that if you test a value that is positive, so let's say we test a suspected root, okay, b, we haven't decided if it's a root yet, but we test it in synthetic division and we find that every single value is actually positive, so we don't even need a remainder of 0. Okay, let's say we do have a remainder but it's positive and every other value here is positive. Well, then we conclude that b must be an upper bound of that equation. So there are no rational roots above b. Okay, there wouldn't be anything else that we'd have to test that's greater than b. Now, on the converse of that, well, I guess it's not really the converse, but also if we were to test b and that value is negative, so we are testing a negative value for a root, and we find that we either have alternating signs, so they look like this or like this, then b must be a lower bound. So b is a lower bound, meaning there are no rational roots below b. So we wouldn't have to test anything less than or equal to b. So let's use that in problem number 1. So find all roots of this polynomial equation. Well, the first thing that we're going to do is use our first theorem here that we talked about, the rational roots theorem. So I don't have a graph. I'm going to pretend like this graph here doesn't exist. I don't know what that looks like right now. I'm just given this equation, which is what your homework's going to look like, which is what your assessments are also going to look like. I'm just showing a graph so I can verify with you guys that we tested and got the correct solution. So pretend like you don't even see this right now, okay? All right, so the first thing you're going to do is list all of your possible rational roots. So the first thing that we have to do is list the factors of p. Remember, p is your constant term all the way at the end. So the possible factors of p here would be positive or negative 1, positive or negative 2. Now I'm going to also list the factors of q, and q, remember, is your lead coefficient here. So that's positive or negative 1, positive or negative 2, positive or negative 3, and positive or negative 6. So these would be all of the possible values for p and q, or I'm sorry, the possible factors of p and q. Now I have to list all of the possible p over q values. So in other words, I'm taking this number here and I'm going to divide it by each and every single one of these values. So my possible p over q values would be positive 1 over 1, positive or negative 1 over positive or negative 1, which is just positive or negative 1. And then the next one, taking positive or negative 1 and dividing that by positive or negative 2 would be positive or negative 1/2, positive or negative then 1/3, positive or negative 1/6, and then now I'm going to take that same, or the next p value, 2, positive or negative 2, and do the same thing divided by each one of these. So I'm left with same positive or negative 2, positive or negative 1, right? And I'd be listing that one again. I don't need to do that here when I divide 2 by 2. And then I'd have another at positive or negative 2/3, and then again one at positive or negative 2/6, which is the same as 1/3. So this is the list of all the possible P over Q values. Okay. So now that we have this list of all of the possible rational roots, what we would now have to do is test each and every one of these values and determine whether or not it's a root. So it's not that this is a hard thing to do. We can test each and every single one of these, but there's 1, 2, 3, 4, 5, 6 times 2, 12 different possible rational roots. And it's just tedious to have to do that. Now, back in the day when they didn't have a graphing calculator and they didn't have, a calculator to do this, they would have to do all of this by hand. So the upper bound and lower bound theorem really came in handy because they could eliminate some of the possible choices. So what they would do in this case is start with the smallest positive value. In this case, it would be 1/6. And they would test using synthetic division whether or not this was a remainder. If they didn't get a remainder of 0, then they would continue on to the next higher value. So in this case it would be, let's see, 1/3. And then they would continue on from here. Now as soon as they got to a number where they ended up with all, so they have a number here that they're testing, all positive values here, including the remainder, this would indicate that you have an upper bound, meaning that the root has to occur before then, and you would be able to eliminate all of the other higher values. Okay, and I'm going to go through an example where we actually do that in a second, but that's essentially what they would do, and then they would do the same thing for picking negative values. So they would start with the smallest, or I'm sorry, the largest negative value. So again, they would start with negative 1/6, and then they would work their way down the list. So they would go to negative 1/3 and so on, looking for, when they finally got to a factor that, or a possible root that would change signs. Okay, this would indicate, if they had all changing signs, this would indicate that they had a lower bound and that no values before that value, so they could eliminate anything that was smaller than negative 1/3 in this case, that could not be a possible root. So obviously we're going to do one problem where we do have to do this, but it's really nice when we have a calculator that's able to just give us a picture of that. So I'm going to come over here now that I know what my possible rational roots are, because you will be required to be able to list all of the possible rational roots. But now that I have a graphing calculator, I can kind of guess exactly which one it is. So I noticed that I have one that looks like it's at negative 1 here. So you would graph this in your calculator, you would find an approximate root, and then you would test. And when I do that with negative 1, I do end up with a root at negative 1 because my remainder here is 0. So now I'm left with this quadratic here, 6x squared minus x minus 2, and essentially now I'm solving this equation set equal to 0 as well. So here it's probably not faster to go ahead and graph that in your graphing calculator. It would probably just be faster to use the quadratic formula. So I would solve this using the quadratic formula now to find the other root. So then after I apply the quadratic formula, I see that I have two solutions, two roots at, let's see, that's 7, 8, so 2/3 and negative 1/2. Okay, so just to verify here, I do have one that looks like it's at 2/3 here and approximately at negative 1/2, so these would be a list of all of my rational roots. So I had one at negative 1, and then the 2/3 and negative 1/2 that I found. So make sure you're always listing all of them. Go back to your first one that you found instead of just listing the last two. Okay, next up, this question asks us to show that there are no rational roots for this particular polynomial equation. Now, we need to get this equation to have integer coefficients, so the first thing I need to do is multiply throughout by 4 to turn this into x to the 4th minus 3x cubed plus 17x squared plus 16x plus 20. Okay, because all of our theorems here only work when we have integer coefficients in front of each term. All right, now that we have this, I'm going to list all of the possible roots. Okay, so all of the possible rational roots, P over Q, would be positive negative 1, positive negative 2, positive negative 4, positive negative 5, 10, and this last one, 20. Okay, over Q, which is just positive or negative 1. So really, my list is just the numerator here, These are all of the possible values for the rational roots. Okay, so here's a list of all the possible rational roots. Now, I want to test using the upper bound and lower bound theorems here, because it's going to save me a lot of time. What I'm going to do is start with 1, the smallest positive value. And I have a remainder here of 51, which means that 1 is not a root. And I also see that I have none of these signs are the exact same. They do alternate here once. So I would continue on and test now 2. Now after testing 2, I see that I still do not have a remainder of 0, so this is not a root either. And so that I would then increase, because I also don't see all positive coefficients here. So now I'm going to move to 4 and test 4. Alright, now after testing 4, I actually see that I have a remainder of something that's not 0, so clearly 4 is also not a root, but all of the signs here are positive, okay, which means that 4 is an upper bound, meaning there are no other possible rational roots that are greater than 4 here. So 4 is an upper bound, and therefore I can eliminate testing 5, 10, or 20. Okay, so that's what I mean about how they could kind of cut down on their work back in the day by testing that way. So 4 is an upper bound. Now, I would now test negative values. So I'm going to test -1, okay, within my polynomial equation. And this time when I test -1, I see also that I have a remainder of 25, which means that -1 is not a root. However, the signs do switch, positive and negative, they alternate. Okay, so because the signs are alternating, that means that -1 is a lower bound for this polynomial equation as well. So that means I can eliminate any of the other choices, -2, -4, -5, -10, -20. In other words, what I just did was eliminated every single possible rational value here, okay, because we took out 1 was not a rational root, 2 was not a root, 4 was not a root, and because 4 was an upper bound, none of the values greater than 4 also worked. So +5 didn't work, +10 and +20. Now when I test -1, -1 is a lower bound, meaning that -2, -4, -5, -10, and -20 are also not possible roots. So because we've eliminated all of the possible rational roots, and 0 also, if I test f of 0, this is also not a root, which means then, because 0 is not included in these values here, that means there are no rational roots here. Okay, so therefore, there are no rational roots. Alright, so that was the answer for problem 2. We showed that there could not be any rational roots because we eliminated all of the possibilities. Alright, now everything that we've been doing so far has been for rational roots. Now for irrational roots, what we're going to do to try to approximate where those roots exist, we're going to use this location theorem. Now what the location theorem says is that if you have, for any polynomial equation of the form that we've been looking at so far, if a and b are real numbers such that f of a and f of b have opposite signs, then the equation f of x equals 0 has at least one real root between a and b. Now, I think graphically this will make more sense than what it says in words, but essentially all that it's saying is that if you have a polynomial, here's your function and here's a picture. Okay, let's take a value here. Let's make a right here and b over here. Okay, f of a in this case is a negative value. So f of a is negative and f of b up here is positive. So because f of a and f of b have a sign change, they have opposite signs, there has to be somewhere a root, a real root in between. And in fact there is here from the picture, right? So that's all that essentially says, that root has to occur between the interval of a to b. It's an open interval from a to b. Alright? So let's use that idea here when we are given this equation and asked to find the roots between successive hundredths. So we're going to approximate using hundredths. Now at first I just want to show you this rule, this location theorem here. I have the graph of this function right over here, and if I were to test f of 3 and f of 4, f of 3 is going to give me a -17, while f of 4 is going to give me a +2. So again, here I have opposite signs. There's a sign change here, which means that a root, a real root, occurs between 3 and 4. Okay, oops, not between, between. Okay, so what we're going to do essentially is try to find that exact location, or not the exact, but approximate that location to the nearest hundredth. Okay, now I'm not going to bother testing a value like 3.1. I know that the value 3.1 is way over here, and just based off of my graph, I'm going to get a little bit closer because I would have to check, you know, f of 3.1, f of 3.2, 3.3, and so on. So I'm going to start with f of 3.7, okay, and I'm going to use a graphing calculator to actually find all of these values. All right, and I'm going to do this fairly quickly with you, but we're going to go up by tenths at first, just so that we can try to find where the hundredths should start to break down. Okay, so I went ahead and I already graphed this, and I have it graphed in the standard window right now, so it doesn't look exactly like our picture because our scale was a little bit different. But really all that I'm interested in is finding these values anyhow, so all I'm going to do is hit second calc and then value and type in 3.7. Okay, so I type in 3.7, I get an output of negative 5.317. I check then the next value, 3.8, and so on. So I'm going to do this for those listed values here, and eventually what I'm looking for is a sign change. Okay, so if I check 3.9, I still get a negative value here of negative 0.611. Okay, so I'll hit second calc one more time and value and type in 4, and this time we get a positive 2. Oops, that was a negative 0.611. Okay, so we get a positive 2. Okay, so this means the sign change here indicates that we have a root between, I'm not going to spell it wrong this time. Did I spell it wrong? No, I can't. I'm looking at the word and it just looks wrong. Okay, anyways, it's between 3.9 and 4.0. All right, which means that now we're going to go up by hundredths. So I'm going to test 3.91, f of 3.91, f of 3.92, f of 3.93, until again we end up with another sign change. All right, so let's test that as well. So second calc, f of 3.91, and we get negative 0.358. Alright, so I just tested the other two here, and I get finally a positive 1.54. Alright, now what this is indicating then, since there is a sign change here, it went from negative to a positive, that the root is between 3.92 and 3.93. So it's on that open interval from 3.92 to 3.93. Now, since it only asked us to approximate using successive hundredths, I'm done with this question. If it asks for thousandths, then of course then I would start again and test 3.921, 3.922, and so on until I found another sign change. So this is how you would get closer and closer and closer to that irrational root. Alright? Next up, and I think this is going to be a lot easier for you guys since it's going to be a lot of review, I want to work with complex numbers real quick, especially dividing complex numbers and simplifying powers of I. Now, when I see 7 minus 8i over 2i, I don't want an imaginary number in the denominator, so I need to get that out of there by multiplying by I over I. So this is just like multiplying by 1. So in the numerator, I have 7i minus 8i squared all over 2i squared. So this just turns into 7i plus 8 over negative 2. Okay, and of course if these could be reduced, I would reduce that, but since this 7 is odd, I cannot reduce this, and so I'm going to move on to 5. Now in 5, multiplying by I over I will simply not work here, because I'll still end up with I plus 3i squared in the denominator, and although this term drops to be a real number, the I is still imaginary, and I can't get rid of it. So what I'm going to do here is multiply by the conjugate. So let's see if you remember doing that last year. When you multiply by the conjugate here, 1 minus 3i over 1 minus 3i, the denominator is really easy because that's just going to FOIL to 1 squared minus 9i squared. Okay, so the numerator is the only thing really that you have to actually FOIL out those terms. So you have, 2 minus 6i minus 4i plus 12i squared. And then you would reduce the rest of this and simplify. So you have 2 minus this 12 So negative 10, and then these two would combine and be negative 10i. And in the denominator, 1 minus a negative 9 turns into 10. It's positive 10. And this would then simplify to negative 1 minus I. Okay, so this is kind of like I was saying in that problem over here. We can't reduce this one, but here we can because each of those factors out a 10. Alright, I would like you to try number 6 on your own and then check with the key. Finally, simplifying powers of I is something that a lot of people find really tricky, but I like it a lot because it's just asking you to basically rewrite using exponents. Alright, let's just go through a couple things here. First, I squared is obviously negative 1. We've been talking about that for a while. Now, I cubed, I could rewrite that as I squared times another I, which is negative 1 times I, which simplifies to just negative I. I to the fourth can be rewritten, however, as I squared times another I squared, or alternatively, I squared squared. Okay, so I squared times I squared is just negative 1 times negative 1, which gives me a positive 1. And negative 1 to the second power is the same as I squared squared, which also gives me a positive 1. Now, instead of breaking it up like this, I'm going to use the power of product of powers rule here and try to rewrite everything in terms of I squared. So this first example here of I to the 24th, I'm going to break that down and write that as I squared to the 12th power because that's I to the 24th. That's negative 1 to the 12th power. Anything to an even power is going to be positive, so this is just simply a positive 1. I to the 23rd, however, is going to be written as I squared to the 11th power multiplied by another I to give me a total of 23 i's. Now this is negative 1 to the 11th power times I. So this here to an odd power is a negative 1 times I, and that gives me a negative I. I'd like you guys to try 9, 10, and 11 just to make sure that you understand that, and I'm going to finish off with number 12, and that'll be the last problem for today, and then you'll finish 13 on your own. Okay, I think I changed number 12 actually. I made this the 8th root of 5, and the I think it's to the 24th power, yeah, so to make that irrational. Okay, so I'm going to essentially just distribute this 24 to both. So I'm going to rewrite this as 5 to the 1/8 power raised to the 24th power multiplied by I to the 24th. So this becomes 5 to the 3rd power times I to the 24th. Now I to the 24th, they did this on purpose. We already evaluated that. But essentially all you would do here is do the same thing you did for 9, 10, and 11. But since I already know the outcome of this, this is just 1. This is 5 cubed times 1. So just 125. Alright? Okay, that's the end of the lesson. Ask any questions that you have in class tomorrow. And nice job.